Right, guys, so group theory was a requested topic for the short notes thing. So I have covered actually the Mulliken symbols, quick construction of character table, normal modes and allowed transitions. All this I will be explaining in this video, which will be helpful for your revision purpose for CSIR entrance, right? So firstly you should able to find out the Mulliken symbol for the given particular characters. In exam you may not get the full character table. They will just give you this thing and they'll just leave this particular thing over here and they'll ask you what is the character table. Many times this kind of model questions have been appeared in the exam. So for the quick revision, what is the thing you have to know to write down the molecule symbol? Let's say if the axis is a principal axis, what is the symmetry element? It is A, and antisymmetric element is B. Okay, what does it mean? See, if 1 is there, it is symmetric. If it is -1, it is antisymmetric. Okay, so here you have A and A. This is your principal axis C2 for C2V point group, right? And it is 1 and 1. 1 is symmetric, hence you write the term symmetry as A over here. Okay, but here you see it is -1 and -1. So your symmetry should definitely, it should be B. It should not be A. Okay, with that you understand that here definitely B will come, right? So here it has to be B but not A, because if the principal axis is antisymmetric, that if it is -1, then the term given is here B. Okay, next, if it is C2 perpendicular to Cn is given, then the symmetry is 1, antisymmetry is 2, but here there is no C2 perpendicular to Cn, so leave that. Next, what comes? Sigma V. Do you have sigma V? Yes, these are your vertical planes. If it is symmetric, it's 1. If it is antisymmetric, it's 2. Okay, so when you look for the sigma exact, here it is symmetric. Okay, so the first one, as it is symmetric, your symbol will be 1. Okay, so here you will get B1. Here it is antisymmetric, so B, and sigma exact it is -1, so again it is not 1, instead it is 2. So this is B2. Look here also it is antisymmetric, so A2, but here it is symmetric, so A1. So what is the answer over here? It has to be B1 to satisfy according to these rules. -1 antisymmetric, it's B, and 1 symmetric, it's 1. Okay, let's say you were not given with C2V point group and you were given with D4, D2H, something like that, where center of symmetry is present. Okay, ethylene molecule or something like that. Then if it is symmetric, you will be writing G-rate. Okay, Ci with respect to Ci. Let's say you have your Ci here. Then if it is symmetric, that means if it is character is 1, you will be giving G-rate. If it is -1, you will be giving un-G-rate. Okay, and then sigma H. Okay, let's say here you have even horizontal plane. Then you have to give what is this, dash? Yeah, a dash for the symmetric thing and double dash for the anti-symmetric thing. So these are important for the revision to write out the Mulliken symbol for a given particular character table. Okay, next what we'll discuss is matrices. This is because I want to even teach you the shortcut of constructing the character table. Okay, using matrices. We have the 4 rules to construct the character table, but that is little lengthy and time taking. So this is useful in many ways, not only just for construction of character table. They may ask you what is trace or spur for a particular given CNZ, C2, C3 or something like that. In that cases, even the matrices are helpful. So I'll construct the character table using matrices. Okay, so for E character table, for the E matrix, what is the matrices? 1 0 0 0 1 0 0 0 1. Okay, it means everything is symmetric. That's why we are getting 1 around the diagonal. So what is the trace or spur, or I can say character, that is represented by chi, is 3 for E matrix. Okay, next C and Z. This can be for C2, C3, C4, anything. A general formula we have, we can write down for our required axis. Okay, so C and Z, you have cos theta, sin theta 0, minus sin theta, cos theta 0, 0, 0, 1. Just mug up this thing. It is very easy if you remember these matrices for the construction of character table. Okay, so remember this way: cos theta 1, sin theta minus sin theta, all other things are 0. Okay, and then sigma xy. Whenever you have a plane along some xy, what happens? The whatever the molecule which is present in the z direction, it will reflect, right? It will reflect. So there will be change. That is, the +1 converts to -1. Whenever you cut a molecule along xy plane, what happens? Whatever is present along the z, it will invert because of the reflection. That's why for xy you will not get -1, only for z you will get. In the same fashion, for yz, you will not get minus for y and z. Instead, you will get x, because if you put a plane in yz, whatever is present in x direction will be reflected to the other side, right? So the x will become -1. Similarly, xz. So y will become -1 if you reflect along xz plane. Okay. Similarly, I, you know, what happens if you apply I? All the elements which are present in one side will go to the other side. Everything is interchanged. So all the characters will be -1 if we consider I. Okay. So these are the matrices. Very simple to remember. Just remember these matrices for the construction of character table, which I am going to teach. And S and Z, it is simple. C and Z into sigma xy. C and Z, let's say C2. So what do you do? C2 180. Cos 180 -1, sin 180 0. Substitute the values, then you get the matrix for C2 over here. And sigma xy anyways you have. So multiply these two matrices, 3 cross 3. If you multiply, you will get a final answer. That will be the matrix for your S2. Okay. So this is the way you have to calculate the matrices. Now, construction of character table C2V. With these matrices, I'll try to explain you. See, this is what we'll get if you do the matrices. E is this, C2 sigma xz and sigma yz. So they may ask you what are the reducible representations for C2V point group. So with these matrices, you can say that 1 plus 1 plus 1, 3. This is -1, right? Like -1, -1 plus 1. -2 plus 1 is -1. Similarly, this is 1 and 1. So these are your reducible representations for C2V point group. Now, I have constructed the character table from this. See, I have broken each matrix into 1 cross 1 matrix. The 3 cross 3 is broken into 1 cross 1, like this I have considered. So 1, 1, -1, 1 and -1. These are my first numbers. Don't look at this Mulligan symbols, okay? Because this you have learned that from the previous page. By looking at the characters, you write these numbers. It's not that you write the symbols and write the characters. So don't look at these things. So 1, -1, 1, -1 are your first characters, and then 1, -1, -1 and 1 are the next characters, and then 1, 1 and 1, and at last 1. These are your another characters. Now you assign the symbols. You know it is here antisymmetric, so B. This is symmetric, so 1. Antisymmetric B. This is also antisymmetric, so 2. This is symmetric A. This is also symmetric, so 1. So now that you have got the 75% of the character table, the last one you have to find out using the basic 4 rules which are given for the construction of character table. And what is that? The second rule is about dimensionality, and the fourth rule is orthogonality. Okay, you know that dimensionality is nothing but the sum of all the characters should be equal to the order of the group. That is 1 square plus 1 square plus 1 square plus 1 square should be equals to order of the group 4. And this square should be 4. So it's matching because C2V order is 4. And then orthogonality. What is orthogonality? If you multiply any two characters, the resultant should be 0. That is 1 into 1 plus -1 into -1 plus 1 into -1 plus -1 into 1. The resultant should be 0. So you, based on these numbers, first you write the dimensionality, you will get all 1, and minus and plus is decided based on the orthogonality rule. Okay, if it is not satisfied here, if I write +1 and I do not get 0, then I have written here -1, so that any two multiplications will give me the sum has to be 0. So on that basis, I even have concluded that these are my characters based on rule 2 and 4. Now it is a perfect character table. And for this, what will be the symbol? This is symmetric. Okay, once it is symmetric, it is A. And this is antisymmetric. So what is the Mulligan symbol now? A2. So this is my character table. I simply do it from the matrices instead of going to the other other procedure which we have in our books. Okay, this is little simple I feel, so I have taken up this thing. And matrices, as I said, is very important. Better you remember all these things, especially C and Z. Okay, this is like you have to mug up. Others are easy to understand, right? Now that you have constructed the character table and you know reducible representations, it's time that you should also know what are the irreducible representations. Okay, so how do you calculate the irreducible representations? Using standard deduction formula, a very important topic expected to appear from the group theory in CSIR. Okay, so to find the irreducible representations from reducible representations, we have this particular formula, that is standard deduction formula. 1 by h summation of g of r chi I of r chi j of r. This just means that these are the group number of this particular what do I say, the symmetry elements. Okay, this is 1, here it is 2 and 3, like that. And these are your irreducible representations, and these are your reducible representations. Okay, so how do you calculate? Let's say this is the point group. I mean, for NH3 molecule, this is the point group. Till here you will be given in the exam. Okay, no problem at all. If they are not asking the character table and they are asking you to find out the irreducible representations, they will give you this character table. What you have to do from the character table, as I have told in one of my group theory videos, that I find this way as most easiest way. Don't follow the book way where the calculation of irreducible representation is very difficult. Just go with this procedure, I'll tell you now. Okay, so first calculate number of unshifted atoms. See how many atoms there, 1 2 3 4. For E is nothing but doing nothing or rotating 360 degrees. So resultant will be the same molecule. There is no shift in the atom's position. So number of unshifted atoms are 4 for NH3 molecule over here. C3. So if you rotate C3, what happens? Let's say I write 1 2 3. On rotation, 1 will occupy second, 2 will occupy 3, and 3 will occupy 1. All the hydrogens will be shifted, but nitrogen remains as such. Okay, it doesn't change its position. So what is the number of unshifted atoms for NH3 on performing C3? It is only 1, that is nitrogen. So it is 1. And then sigma V. So if you apply, if you pass a plane, okay, if you pass a plane like this H2 and H3 will be shifted, but H1 and N will be in plane. So these are only the shifted atoms. So number of unshifted atoms on applying sigma V is 2. Okay, now what you do is, this is the reason matrices. See, character. Here, instead of going to the other way which is present in the book, as I have explained in one of my videos, just calculate the character of these particular groups. E, we know the character is 3. For C3, you just calculate that cos theta sin theta thing. Substitute 120 degrees, you will get 0 as your answer. That is the character of, you have to add the diagonal characters. Okay, don't forget that. And then sigma V, we have calculated, it's 1. The character is 1. So what are your irreducible representations for ammonia molecule? C3V point group is this. Okay, it's not that for C3V these are irreducible. It changes from molecule to molecule. So this procedure you have to follow. 4 3s are 12, 1 into 0, 2 into 1. So these are your irreducible representations for the ammonia molecule. So you may also get what are the irreducible representations for particular molecule. So till here you can do. In some exams they will also give you irreducible representations, and they will give you the character table, and they'll ask you what is the normal modes. How do you calculate the normal modes? So using this thing we have to calculate the normal modes. So here I have calculated. So using the C3V point group over here. So C3V, first we'll calculate A1, and we know formula 1 by H G of R chi I of irreducible plus chi I of reducible representation. So 1 by order of C3V point group is 6. Why? This 1, G of R is 1 into irreducible representation is 1, and reducible representation is 1 and irreducible representation is 2. So 1 into 1 into 12 plus 2 into 1 into 0 plus 3 into 1 into 2. Okay, so this A1 will give you this particular thing, using standard deduction formula. So 18 by 6, 3A1. Next A2. For A2, this 1 into this A2 values into irreducible representation. 1 into 1 into 12 plus 2 into 1 into 0, 3 into minus 1 into 2. That will give me the A2. Okay, the normal total modes. And then E. 1 into 2 into 12, 2 into minus 1 into 0, 3 into 0 into 2. So that will give you this particular thing. Okay, so my total modes come out to be 3a1 plus a2 plus 4e. Okay, but in exam they'll never ask you total modes, they'll ask you normal modes. Now from all this, how to calculate again? Normal mode, vibrational modes. Okay, so vibrational modes is nothing but total modes minus translation plus rotational. Now these are your total modes, you have to subtract the translational and rotational. Now you should know what are translational and rotational again, and they are present in your character table. So this x, y, z are your translational motions, and Rx, Ry, Rz are all about rotational. Okay, so translational and rotational you have to subtract. How do you subtract? First write total modes 3a1 plus a2 plus 4e minus, now where are translational present? A1 and e. Okay, there is no translation for a2. So subtract a1 and e, and then rotational. Where are rotational present? A2 and e. So a2 and e also you just write down. So subtract all this, the resultant will be your vibrational modes, that is normal modes. So this will be asked in the exam, okay, to calculate the normal modes. So what is the procedure? It's very simple. You have to calculate irreducible representation with the shortcut I have given, and apply the standard reduction formula. Use the character table. They'll give you character table, don't worry. If they are asking you the normal modes, they'll definitely give you character table. If not, still I have told you the matrices method. You can go through that method to even construct the character table and then calculate the normal modes, but it goes very lengthy. Okay, don't think don't worry, you will not get that. So with this I calculated the normal modes. What is the another expected question which can come from group theory is the allowed and forbidden transitions. Okay, I have again taken the C2V character table, and I try to explain the allow and forbidden transitions. That is the direct product. Okay, so I have written that ground state into excited state symbol will give you a resultant product which should have some dipole moment. Okay, on applying this a1 and any two operations, the resultant should be one which have the dipole moment along xyz axis. Let's say we have taken a1 and a1. Okay, the ground state a1 and excited state also, let us consider it is a1. 1 into 1, 1 into 1, 1 into 1 and 1 into 1 will give you again the same a1. Okay, so and it lies along the z axis. There is a translation, there is a dipole moment present. So I can say that this is an allowed transition. Okay, we can say allow only when there exists a dipole moment along the xyz axes. Let's say I have taken a1 to a2. So if I multiply 1 into 1, 1 into 1, 1 into minus 1, 1 into minus 1, the resultant will be a2. Okay, as the resultant is a2, just see if there exists dipole moment along xyz axis. No, there is no dipole moment. So I can say that this is not an allowed transition. That is a1 to a2 is a forbidden transition. Okay, and then I've solved for other twos. Let's say a1 to b1. You may be given with any two. You may be given with a2 to b1, b1 to b2, b2 to a1, anything. Just calculate the resultant and then see that if it is allowed along xyz axis or not. That is, I can say that in other words it is an IR if it is allowed, it is IR active. Okay, you cannot tell about Raman just with this particular H2O molecule, because for Raman, for centrosymmetric molecules you will be asked in the exam. For this you will not be asked to if it is Raman active or not, because it is difficult to find out. So for a centrosymmetric molecule they may give you this thing, and they may indirectly ask you if it is Raman active or not. So once you find out that it is IR inactive, this A1 to A2, if it is forbidden, and if it is a centrosymmetric molecule, definitely it will be Raman active. Okay, in that way Raman will be linked. Directly you may not get such a difficult question. Instead, in the other way, he may give you any centrosymmetric molecule, and then he will ask you if that particular molecule is Raman active if you if you do a transition from A2 to B1 or something like that. So in that way you may get a question from Raman activity. If not, this is mostly asked in the exam. Okay, if this is allowed or not, nothing else than that. So this is all about group theory. It was a very requested topic, so I had to take up this topic because yes, it is very scoring. If you have already read this and you are going through this video, I think you are done with your preparation for your CSIR in this group theory concept. Okay, so if you like this video, please do like the video and share your comments, and then subscribe to my channel so that I can build more I can do more and do better in my future days, right? Thank you.